Let's gonna start with this talk. It's about sonic attack to spinning hard drives. And I am Alfredo Ortega. I am a security researcher, developer, whatever, from Argentina. So I come here because of a very short trip, a very nice country. And let's start with the talk because basically this talk is about demonstration. I have like a 5 or 6 demonstrations, maybe not all will work, but that's the cool thing about them, right? Okay, this talk is about measuring audio with hard disk. This looks like a crazy thing, but it actually works quite fine. And you need this setup. This is, I create this setup. It's basically a regular hard disk plugged to a piece of iron that simulates a computer box. Also, this can be done with a hard disk inside a notebook, but it's not so obvious. So to increase the effect, I do it remotely. So also you can see that it's actually a regular hard disk. It's not like a magic trick. So let's go on how this works. This is a timing attack. I mean, if you do security since a while, you can see that timing attacks can be very serious. In the last year, there's a lot of timing attacks. For example, Spectre and Meltdown, they are timing attacks. The problem with the computers is that they are too fast and too precise, and you can measure anything. The way that you basically record audio with a hard disk is measuring the difference of time. It's basically the same side channel that you can use measuring difference in CPU processing or whatever. You can, for any system to be safe, you cannot leak information. There is a variation in timing between in a system that shouldn't be any variation. You can measure and you can detect things. In this case, we can detect audio, but we can detect several other things. For example, well, this is what I was speaking just now. It's very easy to actually measure audio. The hard disks are a very sensitive device. They don't stand a lot of vibration, and audio, as you can see, is vibration. That's why in the server environment, they say that you have to mount hard disk in rubber mounts because they are very sensitive to vibration and audio. The thing that they won't say is that the performance of hard drives actually varies a lot with the vibrations. I mean, if you have in a lot of environment with a lot of vibration, the performance will go down, and we can measure that. I mean, this is super simple. This is C code that you can see down. It's basically all the thing what you have to do. We only need to read a file a lot of times and measure how you will think that this simple read will take the same time every time, and no, that is not, because that's not right. This simple call to read a little file in the hard disk will change. Something will take 100 milliseconds, something will take 1 milliseconds, and this difference is basically the vibration that the hard disk is feeling. So that's basically this. It's very easy. Now, the thing we can do is the first demonstration is about not a hard drive, but about anything else. For example, every syscall every call that you do to the kernel should take the same amount of time, in theory, but in reality, let's do the fast demonstration here. What we are seeing here is a simple call to the kernel to ask from the process number. Is get PID, if you can see. I ask the kernel, okay, give me my process number. So this should take exactly the same amount of time. We plot this time in the x-axis, and the y-axis is the time, and we can see a very interesting thing here. Saying, well, what is this? What is that thing that we are seeing here? The blue part is the spectrum, and the yellow part is basically like an oscilloscope. So that line should be a straight line, but it is not. Because why? Because the kernel have a lot of internal, there are a lot of processes in this computer. and they're firing constantly, and what we're seeing here is basically the kernel load that we are not supposed to see. But we can see it anyway, because the computers are really fast, and they optimize a lot. So every time we see a little line here, it's the kernel waking up to do some additional, some hidden process, for example, the hard disk maintenance or the Wi-Fi card. So we actually can see this from an unprivileged process. And this is basically from every syscall. We can call, for example, we can try whatever syscall we want. I'm sorry, I'm not a very good programmer, so I have to kill it the old school way. For example, we can try with the stat syscall. The stat syscall is just ask for information about a file, whatever file, and we can see there is a different pattern here, but it's basically the same. And we can, for example, let's do another thing in another process here. If we move this window, we should see, well, I don't see very much, but this demonstration is not working very well. But the thing is, we actually are seeing the internal behavior of the kernel that we shouldn't see. And we use this to read things on the hard disk. It's the same thing, but the thing I want to say is this is not only for hard disk. You can use the timing attack to measure all kind of physical, external physical variables. Let's continue with the demo. So this is what we are looking just now. We can. This is basically a security problem. I mean, in the future attacks, people will use this, and we read things into this. They call what is this causing this variation. I don't know what it is, but it's there. It shouldn't be there. Okay, so. Let's do, this is a little graph about the capabilities of the hard drive of a microphone. Of course, it's not a high definition microphone. Actually is very bad. It just listens to the determinant frequencies because it's basically a metal case. It's not designed to be a microphone. Basically, you can use to read low frequencies and some high frequencies, but not much in the middle. That's varies from hard disk to hard disk because of resonance of the metal box, basically. And also, it depends a lot in what the hard disk is screwed on. I mean, you screw on a big metal plate like this, it basically will measure the vibration of all the metal plates, and it will be much more sensitive. This is the setup that I have here. And let's do a demonstration now about how this works. Right? Okay, this is we can measure movement because the hard disk actually is sensitive to movement. The movement is a very low frequency vibration, but the hard disk is very sensitive to it. Vibration and some sound. For example, let's do a demonstration here. I think. Oh, here come the demonstrations. Let's see if it works. I know it worked because I just tested. Okay, now we have a very similar graph, but we are plotting the read time of the hard disk. In the yellow line is basically we do a lot of reads to the hard disk, and every time we are measure, of course the time will vary. Let's see how this works. Okay, look at it, it's quite sensitive. I just touched the hard disk, and it already took a measurement, already sends an audio wave. Also, I can type, it's so sensitive, I can taste the table, probably. Look at that. Actually, we can play some music in here. But that is, the microphone is this, but you can see this is super sensitive to audio. We can tap whatever. Maybe we can clap, but we have to do very strong. I have another test here. This is a speaker that we can actually see how sensitive the hard disk is to frequency. I want to try to do is to apply a frequency here to see which one the hard disk can record. This is a sweep. We're going to do a frequency from 20 hertz to a very high tone. Of course, it has to be working. Okay, so this is an audio wave that is playing. And as the frequency is increasing, I don't know if the speaker is working. Yeah, apparently it's working. Maybe you can see it, you can hear it. I don't know if it is will work, because we need to have to correct a lot of audio here, and these speakers are really not a lot of volume here. For example, let's put in there. Oh, this is working. No, actually the volume was enough. I mean, now the hard disk is completely stopped. It completely blocked because it's entered in a resonance. If I took the speaker, look how it start working. Well, there were some glitches there. The thing is, the hard disk, if the hard disk stopped working, the kernel will eventually crash. I mean, it not will crash, it will disconnect the hard disk. We can see that as the frequency increases, the hard disk is no longer sensitive to it. That's it. It's not so, well, now it's sensitive again. I'm gonna stop this, sorry, because it's hurting my ears. Okay, so what we have here is basically, yeah, it's quite, I used to do it with a song, but this is more like scientific, and I look more strange. We can see this is basically the graph of the frequency response. I mean, for 20 hertz to 20, well, I don't know, I think 2 kilohertz. I mean, we didn't reach 20 kilohertz. But if this were a microphone, it would be a complete straight thing, but it's not really a good microphone. And one interesting thing is, maybe you can see that at one time the hard disk completely stopped. That is because if you find the primordial resonance frequency of the hard disk, I mean, the plate will start vibrate a lot, and the hard disk controller will basically just stop communication. The crazy thing is, it will not just stop communication, it will stop responding to the computer. I mean, it will not respond even 80 commands, you know, the commands from the SCSI command to the hard disk. It will stop completely responding, so the kernel will go a little crazy. We're gonna see that we can actually crash a computer. There was some research that Windows directly, it just blows blue screen. Linux doesn't blue screen, but it just disconnect the hard disk, and we can see in a demonstration here. I won't do a demonstration of that here because I need a very high sound for 60 seconds. That's the timeout of the kernel, and it's really crazy in the ears. But I can do it if you want. Let's continue with the demonstration. This is some crazy things. Because I just realized, well, this should work remotely. I mean, there's nothing that stopped me to log to a cloud server that use hard disk and do exactly the same test. So maybe I can listen to audio, vibrations, footstep, whatever, that are in a remote, I don't know, a data center. I mean, that will work. Well, I tried on Microsoft servers, and I have a video to prove it. I don't want to connect to Microsoft server now. Also, you have to wait until you listen to somebody to step on the data center. Let's see if it works. Okay, I have a video. What I did now, if you can see there, is I connect to an Azure. Azure is the cloud computer from Microsoft. That's the IP, yes, whatever, logging in, I don't care. And I run the same measuring system. I know I'm measuring the hard disk of the virtual machine. Now, the virtual machine actually is virtual, but it uses a real hard disk. So in theory, we can measure audio in the hard disk in the cloud environment. And the thing is that at first, I didn't see anything. I mean, it was several minutes without anything that is understandable because there's nobody in a cloud computer. So this video is actually quite long. You can see here 15 minutes, nothing, 16 minutes. There's some spurious vibration there, but maybe it's the kernel just blocking for some things. And if we go to about 40, you can see we start listening to things. And the thing is, this thing on the side, you can see these red points that is on the right side, that one. Actually, that is like the waveform of the audio variation. And it's different if the kernel is waiting for something and if the hard disk is vibrating. So I can see this is exactly the same waveform that I get if the hard disk is getting vibration. So we are looking here is vibrations in the Microsoft data center. So I don't know what it is. I don't think it's music. I mean, nobody's playing music in that center. But probably some vibrations, some machines start running or something working. So the thing is, this is so powerful. It actually can measure things outside the virtual machine, as long as you have a real hard disk. Because this doesn't work in SSD. So if you have an SSD, you're safe. I tried it. Stupidly, because of course nothing vibrates in SSD. But the thing is, it actually works. You can measure vibrations in a remote data center. It's crazy, but it works. But the crazier thing is you actually can attack a hard disk. You can cause a dangerous survey. Actually, we just saw that. When we reach about 150 hertz, you can see the hard disk stop working. This is basically physics. I mean, you find the resonant frequencies of any mechanical device, you will break it. I mean, you can bring down a bridge with that. So the thing is, you need very little power. I mean, this speaker is only, I don't know, not even a watt. I mean, not even half a watt. Stuxnet actually worked that way. It just found this resonant frequency of this centrifuge and just they blow away. So we can do it with the hard disk. Yes, we can do it. And I have another demonstration. I won't do it here because I don't want to spend a different hard disk every time I do this demonstration. But I have it in video. So this is the sound. You know, it's very loud. The hard disk here is just stop responding to the kernel. And if you can see here, I just did a command to the kernel asking from hard disk, and then we can see there is the kernel basically disconnect the hard disk. It just doesn't exist anymore because the Linux kernel, you can see the errors. They say that this is the kernel saying that dude, the hard disk is not responding anymore. It's not responding anymore, and after a minute it just disconnected. And it doesn't work anymore. I mean, the only thing you can do it is to reboot the machine, and it will recognize the hard disk again. But of course, you can damage the hard disk. I mean, I damaged a lot. I mean, with enough volume, you can destroy it very easily. They are very sensitive devices. I mean, the idea is that actually you need very little sound to do it. I mean, of course, you do have a bigger sound. You can really destroy a hard disk very easily. Let's see a demonstration, of course. Okay. Now I use a song here so we can actually see the beats. I know you can hear it. That's the 1,000 watt speaker. I'm increasing the volume, you can see it. But the hard disk actually stopped working. But that's really not unexpected. I mean, if you put a 1,000 speaker, the hard disk, it will basically destroy itself. But the thing is, you can do it with a 200 milliwatt speaker. That is basically the new thing that you can do this. I did several cases when alarms going on in data centers and blowing up the hard disk and completely destroy them. So let's go into speak about similar work, because this is not actually previous work, they're actually a posterior works. I presented this research about in Argentina in about 2016, I think 1 year ago or a couple years ago. And they were, after that, there were much better research. They were more truthful. I mean, they measured things, they actually build models, and they well discovered the same thing basically. If you blast a hard disk with audio, you will destroy it. No surprise here. This is from the Michigan University. It's called Blue Note. They, I think they didn't cite me. I'm not angry about that. Of course not. This is another from Princeton. It's the same thing. Basically, they did a very nice model and discovered the same thing. The measurement actually matched what I did. I did it much more, and not really scientific environment, but the measurement actually matched pretty well the same frequency. Also didn't cite me. It's okay. Bastards. And well, basically, that's it. We have a lot of the problem here is basically a timing attack. The kernel should not be able to allow you to measure time in such a precise way, because you can do this. This is only the beginning. You can measure whatever you think. I mean, you have Wi-Fi. You can measure position, measuring the variations on the Wi-Fi signals. What can you do? You can measure a lot of things. I mean, there are timings attack in everything. There is a way to fix this. Yes, at least to unprivileged users, you should make high-resolution timers available. This actually is starting to work. I mean, browsers, I think JavaScript doesn't allow a high precision timing anymore, because they know that there are a lot of timing side channels there. But you still have problems with computers and unprivileged process and with cloud environments, because this actually, as you can see, actually work perfectly in cloud environments. And well, that is a fine way to destroy hard disk also. Well, I think that's basically it. Thank you.
You think it may be possible to, with a predetermined sequence of sounds, you could write data on that remote hard disk?
Your question is if I can, using sound, modify the content of the hard disk. I don't think you can, actually, because a hard disk is a very complex device. When you write a byte, you have a error correction code. I mean, you have to first find a way to write into the magnetic plates in such a precision that you can actually write a complete sector with the correct, the error correction code correct, and that is quite unlikely. I mean, this is basically hitting the hard disk with a sledgehammer. It's not very precise tool. I mean, it's precise enough to measure audio, because audio is very slow. And actually, it's not very good at that either. I mean, you can see that you can measure vibration, basically, like steps. I cannot measure voice with this yet. Maybe in the future I will find a way. But no, it's a very raw technique. It's not so precise to write things, but you never know.
The data of inside the drive are destroyed, or just the hardware?
Sorry?
The data inside the driver is wiped? Isn't more data inside the driver, yeah, or just the driver are destroyed?
No, the data inside the driver is relatively safe. I mean, it's not safe because the plates are vibrating, and eventually it will destroy the data. I mean, I have a Samsung hard, a couple Samsung hard drive. It won't work anymore. They do a strange noise, like click, 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 click. It just completely is fuck up. But I don't think it's the plate. It is like the head. The head is destroyed because the head is very sensitive. The head punch with the hard disk. The thing is, when the hard disk first detects a vibration, it just packs the head automatically, and very fast, very quickly. So the data actually is safe, but the head starts bouncing around, and eventually it will just get banned or destroyed. I don't know what it happened, but it just don't work anymore.
Thank you.
In a data center, how does it affect the sound of the fans in the room?
Yeah. Well, the fans has very, very low sound.
Very, very low.
It's too low to affect, but depends with the fan. But actually, you can measure that if you have a very high, you have a lot of noise in the data center. The hard disk will work slower. That is something that is in the data sheet. I mean, there is a very old video of a guy screaming at the hard disk. And the hard disk basically starting to decrease in the throughput. I mean, they're very sensitive. So if they're a regular ceiling fan, it doesn't happen. But you have a big fan, it basically will affect the performance.
The speakers that the notebooks can damage or reduce the lifetime of the hard disk?
Well, I did some tests, and it will depend on the speaker, of course. But I did some tests with a ThinkPad, and I couldn't make to completely stop. But it did affect the throughput. I mean, if you measure the throughput of the hard disk, about 10 megabytes per second, and if you put the speaker at the top, it will decrease. So it really affects. I mean, the speakers can actually affect the hard disk of the safe notebook. But the thing is, ThinkPads specifically, the hard disks are very well mounted. They are mounted in a rubber box. You can open it. So probably if the notebook is another construction, it will be even more sensitive. I mean, in a ThinkPad that is rubber mount, it affects. So maybe in another notebook, it will be worse.
Thank you.
I have a video of that on YouTube. You enter my channel, I have a notebook, and you can measure how the hard disk gets slow.
Have you tested with a hybrid drive, like those that have a little SSD inside?
Hybrid with what? Sorry?
Hybrid, and those hybrid HDDs with a little SSD inside.
Yes. Yeah, I didn't try. You asked if I tried this with a hybrid hard disk. I have a plate and I also have a SSD. No, I did not. But the thing is, basically, an hybrid is a big cache. And this hard disk, I also have a cache in RAM. I mean, the thing is, I did is, but you have to bypass the cache by reading enough. If you read a big file or read a lot of sectors one after the other, eventually the cache memory will spend. I mean, no matter if you have a cache as a flash memory, it will completely fill up. And when it fill up, it will start using the plates. And then you can read audio anyway. I mean, you can bypass the cache memory. Yeah.
Regarding the frequency, is it possible to run a DOS attack running extremely low frequency without human beings noticing this attack?
That's an awesome idea, actually. That's a very good idea. And it's very likely that you can. But I don't know really. It should depend of the resonance of the hard disk. But we can see that the hard disk has several resonance frequencies. Maybe one of them is an ultrasonic range. That's a very good question. Well, actually, in a slide I did a very crude plot of the frequency spectrum. This is the first that we can see here. Is this one. And we have a couple of disks here, one of 2 inches and the one out of 3 inches. I should use more points here. Actually, my science professor will kill me with the block. But there really is an ugly spectrum. I mean, but we can see that it's several peaks. And that is because the hard disk is not, they have several metal parts. It's a very complex device, and each one resonates at a different frequency. So, but one of them is very likely in the ultrasonic one. That's a good one. Thank you. Thank you.
Hi. I was going to ask about the spectrum also, but have you been able to reconstruct some kind of waveform from from what you're reading, or something like that?
So you ask him if I can reconstruct sound
Yeah.
by that. Well, I did some tries, but I didn't play here because it sounds awful. It's not very good. if you can see here, if I play the demo again, it's very easy to do. You can see, but it's not very, it doesn't have a lot of resolution. And I try some reconstruction. I try not to write my password in front of you, sorry. There you go. So you can see here that it looks like it's ready now, but it's very low resolution. So I have about at the sample rate, if you can do an analogy to a sample rate. A regular microphone has a sample rate of 8 kilohertz, the minimum 8 kilohertz, 8 to 44 kilohertz, whatever. This is about 100 hertz. So it's very low sample rate. Does not mean that you can reconstruct anything. I mean, you can use the correct algorithms, you know, whatever new data science can come out. You can reconstruct stuff with only 100 hertz, but it's very low. And but maybe you can increase using another techniques, but I still didn't do it. I tried to reproduce, and the sound is very awful, so I don't even show it to you.
And how about exfiltrating data by sound pulses? Have you tried?
Are you speaking about exfiltrating data from what? From the hard disk?
From other machine, maybe. Because you could encode in sound pulses, I don't know, let's say it resonates at 100 hertz. So you can do like small swaps of 100 hertz, and you could encode it like longer swaps or shorter.
Yeah, sure. You can do it very easily. I mean, it won't move very fast, but you can filter the password in under 1 second. So you need basically a computer that can process a sound and a sensor. I mean, this is basically communication theory. You can, of course, you can do it.
So as long as the computer has a speaker or something, you could perhaps exfiltrate data.
Yeah, they can do like a eye gap channel. That we were talking about eye gaps computer, where you can jump an eye gap.
Because you know which computers has speakers? E-voting machines. They have speakers.
Oh yeah, I like how these two talk get together. That's a great idea. You should do that also. Actually, yeah, in ultrasound, like the guy did.
Mais alguém?
Okay. Well, thank you very much.